Hello and welcome to the converter control lesson. In this lesson, we'll cover the different ways you can control converter models, and we'll explain how to set up and use the different control methods. There are four main control options which can be used for converters in our software. The first one, digital input per switch, is available for every converter in our converter library. The other control options, digital input per leg, internal modulator, and model control, are available for most converters. You can select the control method in the properties window of each converter by changing the control property. When changed, the rest of the properties in the window will be updated according to the control option you've selected. If a converter can only be controlled by digital input per switch, the control property will not be accessible. Let's start by going through the first converter control option, digital input per switch. As the name suggests, this control option relies on external digital signals, which are usually provided by a hardware controller or another external control device. To use your converter in a controller hardware in the loop configuration, you have to connect your hardware controller to the HIL device. You can identify the appropriate digital inputs on the HIL device by referencing the I/O pinout in the Materials tab. For each converter, all available switches are listed under General Properties. Each switch must correspond to the specific digital input where the gate drive signal will be sent. Notice that switches have specific name designations, which can inform you of their position in the converter topology. If you are unsure about the position of a switch in a converter topology, pressing the Help button for the converter will lead you to that converter's documentation. There you will find all relevant information, including the topology schematic. The final part of setting up gate drive signals is defining their active state logic, meaning we define whether the switch will be on when the gate drive signal is high or when it is low. You can set the desired logic for each switch in the drop-down menu on the right side of the property window. In addition to gate drive signals, we can connect an additional digital signal which will enable or disable the gate control of the converter. The next control option is digital input per leg. Assuming the gate drive signals of a given leg are complementary, meaning when the top switch of the leg is on the bottom is off and vice versa, this pair of switches can be controlled using only one digital signal. The advantage of this control method is that you can reduce the number of digital signals required for controlling the converter. The hardware setup procedure is the same as it is for the digital input per switch control option. The difference is that now we only configure one digital input per each leg. By default, high switching logic is used. This means that the active digital input turns on the top switch of the leg while turning off the bottom switch and vice versa. In addition, we have to define the dead time duration. This ensures that the top and bottom switches will not conduct at the same time. To precisely measure dead time, a PWM channel is needed. It's important to consider this when estimating how many converters can fit on one device. When we use this control option, we need to be aware of PWM channels utilization in addition to power electronics converters utilization. The switching enabled property is also available for this control option, as it is with a digital input per switch control option. This allows us to enable or disable the gate drive control according to a selected digital input. The two control options we've covered so far are used to control converters from external devices. The next two control options are typically used when developing the entire control algorithm inside the model, though these can be used for external control as well in some specific applications. The first control option of this kind is internal modulator control. This control option is primarily used when a converter is controlled from inside the model. When you select internal modulator control, the converter component will display input ports for the reference signals, as well as an additional input for a signal which will enable the converter. The number of inputs for reference signals depends on the number of legs of the converter. Internal modulator control utilizes a HIL hardware resource called PWM channels. This hardware resource was presented in Lesson 3.1 Model Mapping, where it is explained that there is a limited number of PWM channels available to us in the model. The PWM channels resource is a multi-channel PWM modulator with a dead time generator and a symmetrical triangular carrier with frequency ranging from 100 Hz to 500 kHz. It has a dedicated slot on the FPGA, and it operates at the frequency of the device's clock, which is 160 MHz for most devices. For the newest generation of HIL devices, the HIL 606 and HIL 404, The clock frequency is 280 MHz. There are multiple components that can utilize the PWM channel's resource. The first is a converter with the digital input per leg control option, as mentioned. The second is a converter with the internal modulator control option. Last is the PWM modulator component, which will be discussed at the end of this lesson. When we use the internal modulator control option, reference signals are provided to the converter, while the carrier signal is generated by the PWM channel's resource. Based on the comparison of the two, the GDS signals are generated. When the control option is set to internal modulator, general properties of the converter correspond to characteristics of the carrier signal. As you can see in the properties window, you first define whether the carrier signal has a fixed or variable frequency. If the carrier frequency is fixed, you can set it directly in the property window. If the carrier frequency is variable, you can provide its value externally using the additional input created on the converter component. This enables the use of control algorithm that require the control frequency to change in real time. A component with an additional input for the carrier frequency is shown below the General Properties window. The generated PWM signals also have a dead time period that can be configured by adjusting the dead time period property. Other properties are carrier phase offset and maximum and minimum of the reference signal. These parameters are visually explained on the picture below. The carrier phase offset is an angle of phase displacement, in degrees, of the carrier signal. Maximum and minimum of the reference signals are the maximum and minimum values of the carrier signal. Some converters with the internal modulator control option, such as the IGBT leg and single-phase inverter, can also have variable carrier phase offset. If this option is selected, an additional input will appear on the converter for the phase offset. This feature is useful when a control technique is based on changing phase offset between carrier signals, such as phase shift modulation. Let's now move on to the last available control option, model control. When the control option is set to model, a signal processing input is created at the top of the component. This input receives a vector of control signals for all of the converter switches. This slide shows a three-phase inverter with the control option set as model. Since the converter receives the control signals in vector form, the individual control signals for each switch are concatenated using a bus join component. Control signals in the vector must be sorted in the same order as they are presented in the Properties window when the selected control option is digital input per switch. One advantage of this control option is that, in addition to creating your own custom control algorithm, you can design your own carrier signal. This functionality is not fully possible when using internal modulator control. In addition, the model control option is useful for control algorithms where you directly control the states of the converter switches, such as finite control set model predictive control. The primary disadvantage of the model control option is that the execution rate of the control algorithm is limited by the capabilities of the CPU depending on complexity. Control algorithms may not be able to execute at a rate faster than 20 to 100 microseconds. This also depends on the HIL device used, since the HIL 404 and HIL 606 have greater CPU capabilities than devices from previous generations, and can perform signal processing computations much faster than other devices. When pulse width modulation is used, an execution rate of 20 to 100 microseconds may be insufficient to generate high-frequency carrier signals with adequate resolution. Therefore, it is highly recommended to use the internal modulator control option for carrier-based modulations such as the pulse width modulation technique, especially for switching frequencies over 10 kHz. We have now reviewed every available control option. For more information and a more comprehensive explanation of the control options, please refer to the converter's documentation listed in Materials tab. Now, let's cover some topics that are closely related to the converter control options. First, let's discuss PWM modulator component. As mentioned previously in this lesson, the PWM modulator is one of the three components in the Typhoon software which utilizes the PWM channel's resource. In most power electronics applications, the HIL device is used to simulate converters. What may be less obvious is that the HIL device can be used as a controller for a real, physical converter as well. With this purpose in mind, the PWM modulator was made available to Typhoon users as a standalone component. It uses the same hardware resources as the internal modulator inside converter components, but it allows access the PWM signals directly in SCADA and at the HIL device's digital outputs without expending resources on a converter model. The properties of the PWM modulator match those of a converter with the internal modulator control option. However, when using the PWM modulator, we can increase the number of PWM channels up to 12. This means that we can have up to 12 carrier signals generated in the PWM channels component, all of which can have separate variable frequencies or phase offsets. If you are interested in a more comprehensive explanation of the PWM modulator and its properties, please refer to its documentation, which is linked in the Materials tab. While Typhoon developers are working on adding the internal modulator control option to every converter in the converter library, some converter components don't yet support this. In these cases, it is possible to use an alternative method that consists of looping back control signals to the converter from the PWM modulator component. A comprehensive explanation of this technique can be found on the FAQ article, "What should I do if a converter does not have an internal modulator?" which is linked in the Materials tab. Before finishing this lesson, there are two additional features worth mentioning. The first is C-code export. If you have developed a controller model using signal processing inside of Typhoon HIL software, you are able to export the controller model as C-code. This allows you to deploy the controller code onto a C-based development environment, like many microcontroller platforms. If you are interested in this, please take a look at our tutorial, How to Export Generic ANSI code, listed in the video description. The second feature is related to the internal modulator control option. Although the internal modulator control option is primarily used when controllers are being developed inside the model, you can also interface an external, high-level controller this way. For example, a PLC controller may be running control loops and outputting analog reference signals. These reference signals can be read by the model using analog inputs and provided directly to a converter with internal modulator control option. This concludes the lesson on converter control methods and techniques. The next lesson series will cover additional features of converter models. Thank you for your attention.